What's up, party people? Let's talk about two-way between subjects ANOVA. So when does one do a two-way between subjects ANOVA? Well, there's specific data circumstances. Those data circumstances are the following. You have a study with two independent variables. The independent variables can be ordinal or nominal. And you've got a single dependent variable that is measured on a interval or ratio scale. So why do I really teach you this? Just like last week, you want to know ANOVA in case your dissertation committee throws some shade at you and says like, hey, you didn't adjust for this, or your effects could be due to this, or you could have not found a difference due to this. You now know how to deal with that with the ANOVA. You can say, yeah, I'll adjust for that. This is a similar situation. You go to your dissertation committee with a really simple design, just a one-way ANOVA, and by the time you leave that office or that room, you've got a second independent variable, and you're like, what do I do? Well, you do two-way between subjects ANOVA. That's what you do. That's why I'm teaching it to you. So two independent variables, that's the key. So here's an example. So let's say you were going to look at the interaction of therapy and sex on depression treatment. So two independent variables. First one, here's your hypothesis. It's just two-tailed. You say, do men and women have similar results from CBT therapy for depression? Independent variable one is therapy level. Excuse me. Which your two levels are no therapy versus CBT therapy. And again, those can be randomly assigned, so that could be a true independent variable, true experimental one. Your second independent variable is sex, male, female, and you can't randomly assign that, so that's going to be a quasi-experiment. So overall, this is going to be a quasi-experimental design. Those are your two independent variables. Your dependent variable, let's just say it's depression. You're going to use the Beck Depression Inventory Screener to measure depression 6 months after the start of the study. One group got therapy and one didn't, half men, half women. So when you do a study with two independent variables, things start to sort of escalate and get big fast. So you got a lot of different means involved in this. So below is words where there would normally be means, but let me take you through this quickly. So on the left side, you've got sex levels, male, female, in a total row. Up top, you got therapy level, no therapy, therapy, and you got a total column. And then where two things hit each other, you've got males, no therapy. That's going to be a group in your study. You have to recruit people for that. You would also have males in therapy. You would need to have females in therapy, or excuse me, females no therapy, females in therapy. And then those are like what we call the crossings, or the cells that are created by your two independent variables at the same time. But then you have these other effects sort of on the peripheries, or on the outside. So you've got an effect that just is all males versus all females. That could be a thing you find. And on the bottom, you've got, well, maybe overall therapy is better than not therapy. That's also an effect you could find. So lots of stuff. And then, the bottom right-hand corner is just the overall mean for everyone in your study. So that's like the things we were calculating last semester. But just to show you. So continuing with the example, do men and women have similar results from CBT therapy for depression? Let's say you plotted those means, whatever they were, and this is what you got. So a higher score on this scale means more depressed. You've got a red line that is males, and you got a purple line that's females. And going from left to right, you start no therapy on the left, therapy on the right. So let's ask some questions about the relationships among these means, because that's basically what this analysis does. So was there a consistent effect of therapy across sexes? So, do you see anything that's obvious, sort of that suggests that, overall people who had therapy just did better? I would say no. I don't see any sort of like real clear pattern in here showing that, therapy was beneficial for all. So how about, was there a consistent effect of sex across therapy levels? So, meaning were men or women, one sex, consistently more or less depressed than the other sex, regardless of whether they got therapy or not. So I would say, note that the purple line there doesn't go as low as the red line. So if you were to average those two dots and get the average depression level of females and compare it to the average level of the two red dots, males, you might find that the average of the two purples, because it goes higher and doesn't go as low as males, you might find that there is, on average, women a little more depressed. So I would say perhaps. And we're not doing any fancy tests yet. And then finally, sort of the big test, the reason people do this analysis, was the effect of therapy different across sexes? So what this one is actually saying is, that, note the other ones were consistent, inconsistent. This one says, was the effect of one independent variable different for the levels of the other independent variable? Did therapy have a different effect, or was it a different impact for men and women? That's sort of clearly shown in this plot. So I would say yes. Looking at the plot, so let's start with men. So on the left side there, where they're not getting CBT therapy, they've got a pretty low depression score, right? So higher on that y-axis is more depressed. On the right side for men, you see that it actually goes up. They look like they were more depressed when they had to go to therapy than when they didn't. Now, the opposite appears to be true for women. You've got an effect where when they didn't get therapy, they seem to be more depressed. They were less depressed when they got therapy. So the effect of therapy had a different impact on men than on women, and that's something we call an interaction. That's the co-effect of two independent variables at one time. Or another way to say it is the effect of one independent variable differs across the levels of the other. All right, so that was sort of a theoretical example. Probably not going to be your dissertation, but here's a real one. This is a dissertation someone actually did after school. So they wanted to look at the interaction effects of the co-occurring effect of two independent variables. One of them was sex, and one was being bullied as a child. So she looked at the interaction of sex and childhood bullying on hostility in adults. So it's actually their hostility levels at adults. They completed a questionnaire, but she asked them, "Hey, were you bullied?" I think she just said yes, no when you were a child. And so there's some bullies. So a hypothesis might be, does being bullied as a child have a different effect on males and females' levels of hostility in adulthood? Again, you've got two independent variables here. You've got sex. So you've got sex with two levels, males and females, and you can have 3, 4 levels. I'm just trying to keep it simple for discussion. And then you got this other variable that's whether they're bullied or not. And you might recall you got to come up with some sort of name. She picked bully victimization, or childhood bully victimization might even be better. And then her dependent variable was level of hostility as an adult. So she's positing that these things way in your past impact how you end up as an adult. So let's keep going with that study. She recruited 178 participants. She asked if they were bullied during childhood in school, asked their sex, and they were assigned to one of 4 conditions based on their responses. And this is truly a quasi-experiment. You can't randomly assign people to their sex nor to being bullied as a child. So do note that in these ANOVA designs that have more than one independent variable, you end up with what we call cells or study groups. So if there's 2 levels of one variable and 2 levels of the other independent variable, it's 2 times 2 is 4 cells in the design. What would they be like in her study? Well, here they are. So on the left, you've got bully victimization. People were either not bullied or bullied. The columns are sex. You've got males and females. So where the level of one independent variable intersects with the level of the other, you have what we call a study group or a cell. And doing these designs, you do have to get enough people in every cell in your design. So first cell, for example, is males who are not bullied. Got to get those. Females who are not bullied. Males who were bullied, and females who were bullied. So every one of these sort of intersections is what we call a study group or cell in a design, and it's literally you take 2 times 2 is 4, you got 4 cells. If you had independent variable 3 levels, it would be 2 times 3 or 6. 6 cells. All right, so you also have what we call your marginal effects here. So on the right side, you've got total. So if you were comparing the 85 people to the 93 people on the far right, you would be comparing the overall effect of those who are not bullied to those who are bullied. It would be like a t-test. And that's a particular effect that you get out of these ANOVA designs called a main effect. In this case, it is the main effect of bully victimization. It ignores the other independent variable. Similar on the bottom there, if you compare those 81 people to the 97 people in the hostility, what are you comparing? Well, you're comparing all men to all women, regardless of whether they're bullied or not. You're pretending that other variable isn't in here. So lots of cells in these designs. In the bottom. All right, keep going. So one way you could theoretically analyze the data in the study is you could perhaps do 2 separate independent samples t-tests, right? You got independent variable with 2 levels. Normally we would use a t-test for that if that was the only one in a study. And then you could do a t-test for the other independent variable as well. The dependent variable is the same at both those. So one would be the effect of sex on hostility. You're just comparing men and women to see who's more hostile. The other one would be the effect of being bullied or not, so childhood bullying on hostility. So theoretically you could do that, but that is a bad statistical choice for various reasons. But hopefully you remember statistical validity from last semester. It messes up your statistical validity. Here's 2 reasons why you don't want to do separate tests. First, and probably most important, is what I would say the interaction hypothesis. You want to look at the combined effect of both independent variables. You want to know, okay, this has this effect, the other variable has its own little effect, but together they do something totally different. That's called an interaction hypothesis, and you are most likely interested in studying the combined or interacting effect of your independent variables, in this case both sex and childhood bullying. The t-test approach, it's literally just 2 completely separate tests that pretend the other independent variable doesn't even exist in your study, and so you don't even get to look at that effect if you use this incorrect approach. The other one is kind of like last semester. You got type 1 error inflation. So you do 2 tests. Each of those tests has a 0.05 type 1 error rate. Together, you end up with a 0.1 type 1 error rate or a 10% chance of rejecting the null hypothesis when you shouldn't. So what's the solution? Well, the solution is pay attention. Do this 2-way ANOVA. If you do the 2-way between subjects ANOVA, for example, this 2 by 2, you'll find that it's going to simultaneously evaluate all possible effects of the independent variables, and that includes their combined effect. So each of their individual effects plus their combined effect at the same time. So, not shockingly, there are some assumptions or things that should be true in order for the stat to give you a statistically valid answer. So these are those assumptions. First one is the same assumption for all between groups designs. You've got different people in the cells of your design. So that's what we call independence. They're not matched, paired, same people, repeated measures, etc., different people. The other one is the same for all independent designs. You've got normality. So whatever your dependent variable is, in this case we're talking about hostility scores, and you got 4 cells in the design. The assumption here is that the distribution or shape of those hostility scores, bullied males, not bullied male, bullied females, not bullied females, the shape of the scores in each of those cells, if you plotted it, is approximately normal. And again, we checked it using the skewness value. So if you violate that, as long as it's not crazy Z, it doesn't mess up the ANOVA that much. So you're probably okay, but you can always, send me an email. So continuing with the assumptions, the third one is, again, what it always seems to be in these between groups designs. It's homogeneity of variances. Instead of just homogeneity of variances, I put across the cells because it's not just two groups anymore, right? Now in a 2 by 2, you got 4 groups, and a 2 by 3, you got 6 groups. So it says basically the spread of scores for every cell, and the scores here are the hostility scores. The spread of those scores, it's pretty similar across all the cells in the design. So it is the same assumption as for t-tests in one way ANOVA, but you've got more than just 2 groups in this one, so it helps to say across all the cells. So how do you test that? The usual, there's a homogeneity test along the way that we'll use. If you violate this assumption, this is one that it really does mess up your type 1 error rate. It causes problems with using this particular ANOVA design. So turns out there is no backup test. There's no weed whacker test, if you remember from last semester. So what do? You just like give up? No. So just honestly, what most people do is they probably don't even test the assumption, which is wrong. But what you can do, and I would say, yeah, that's a good idea, is just use a more stringent alpha level. So instead of 0.05, just use 0.01. It makes it harder for you to reject the null, which in its own way reduces your type 1 error rate. All right, so there are 3 different effects that are involved in a two-way ANOVA. With 2 independent variables, there are 3 possible effects in the ANOVA analysis. There is what we call main effects, or effects that are based only on one independent variable. So there's one main effect for each independent variable in the study. So in this case, there's an effect of sex, or a main effect of sex. That is there an effect of sex regardless of the other independent variable? So it's combined across levels of the other independent variable. So there's also potentially a main effect of bullying. Saying, probably the obvious one here is, people who are bullied, regardless of whether they're male or female, they just tend to be more hostile than people who aren't bullied, or vice versa. Like, who knows how it would turn out. But it says, there's just this overall effect. It's just the effect of this one variable. Then you got what we call the interaction. And the interaction is the combined effect of both variables at the same time. So the two-way interaction of independent variable A and independent variable B. So the effect of the independent variable differs across the levels of the other independent variable. So given that you've got these 3 effects, and there's also a lot of means. So for each of the effects above, see if you can figure out what the means are that are being compared. So the effect of sex says, I'm going to pretend that bullying isn't even a variable in the study. I'm just comparing hostility of men versus hostility of women. And if you look, you should see those at the bottom row of this table. You got 9.15 versus 8.67. The main effect of sex in this study would compare the overall average hostility of men versus women, and if it's significant, there's some sort of overall effect of sex. The next effect is the main effect of bullying. So where in this table do you see means that ignore the fact that there's males and females? It's just saying, look, here's all the bullied people. We're going to compare them versus all the not bullied people. So hopefully you see that over on the far right, the total, because that's where it's at. So you got the overall hostility of people who were not bullied was 8.27. The overall hostility of people who were bullied was 9.45. It's a little higher. Is that significant? I don't know. That's why we have the main effect analysis that this ANOVA will do. So there's still a lot of means in this table, right? So these other means are all involved in the, well, except one, I guess, bottom right-hand corner, are involved in the interaction effect. So this is where you got a 2 by 2 or 4 cells again in this design. So your interaction, when you name a group, you have to name both variables at the same time. That's how you know you're looking at an interaction mean. So that first one is not bullied males, going to the right there. Then you got not bullied females, 8.67. Then you got bullied males, 10.40. And then you've got bullied females, 8.67. You might note those two means are literally exactly the same. They're both 8.67. So that's interesting. It is not a typo. So there's also, because there's multiple effects and multiple independent variables, you also have multiple sources of the variability. So things that can explain why the dependent variable varies among participants. So this beach ball looking thing sort of shows what the different effects or sources of variability associated with effects are in a two-way ANOVA. So where do we start? So the different pie slices represent the percentage of variability in the dependent variable that can be accounted for by either the main effect or the interaction of independent variables. So these are the measures of effect size we've been calculating for ANOVA, one way between subjects, repeated measures ANOVA. We did omega squared for t-test, but remember we would always say this effect size represents the proportion of variability that can be accounted for in the DV by its relationship with the IV. So that's all these are. It's what piece of the pie chart can be accounted for by each variable in your study. So this kind of gives you a way to talk about like which of the independent variables in the study were the most important in terms of adult hostility. That's where you would use those effect sizes. More variability accounted for, probably a more important variable for hostility. So the variability in hostility is represented by the whole circle here. This is the beach ball. It's like any pie chart, right? 100% of adult hostility is represented in there. Our first little pie chart chunk is differences that can be explained by sex alone. There's just an overall difference between men and women. That variable alone can account for that chunk of the pie chart. Here I put 10%. Then you also got your differences that are accounted for just by bullying. That's your main effect of bullying. So, regardless of other things, people who got bullied, they're just a little more hostile than people who didn't, or vice versa. Maybe it makes them nice. I have no idea. But, here I just said about 5% of the variability perhaps can be predicted by that or account for. And then finally, you got that third accounted for variability, which is not the effect of just one and not just the effect of other. Notice it's got its own little pie slice here. This is both variables together have like an additional percentage of variability that can be accounted for beyond just what each one of them can do alone. This is what makes this analysis cool, is you actually look at the combined effect of two variables at the same time and you get stuff. So note that the biggest chunk in this pie chart is still just, I don't know why their scores vary, it's just error, right? So that is actually represented by the error in your ANOVA tables when we write those things up. So it's just all the other sources, why people are more hostile than others. So we don't know. This study's only got these three variables in it. So let's talk a little bit more about main effects. This is a new term for you guys. So here's sort of the definition. It is the effect of each IV on the DV without taking the other IV into consideration. So it's the effect of one variable ignoring the other one. Independent variable, sorry. So for example, what effect does being bullied have on hostility in adulthood without taking sex into account? So we're just giving people hostility. We're seeing how much hostility can predict how much they're, Lord, how much being bullied can predict in their adult hostility. So this is the kind of thing we've done in the past, right? This could just be a t-test, probably independent t-test specifically. And you can do one of these for each DV as we talked about, but again, you don't want to do that type 1 error inflation, and you don't get the cool interaction hypothesis. So in this example, but you still do get main effect analyses in your study. So in this example, you might hypothesize that people were bullied. They're probably going to be more hostile as adults than people who are not bullied. That would be a main effect hypothesis. Note what's not mentioned in this hypothesis, the other independent variable. That's kind of how you know this hypothesis is about main effect, not an interaction. So there are multiple comparison tests for significant main effects, just like when we did one-way ANOVA. So because the IVs in the example that we're going over now only have 2 levels, if you get a main effect or a significant main effect, you know that, hey, there's only 2 levels here. I don't need to go do like a Tukey or something funky to figure out exactly who differs from who. There's only 2 means. So if it's significant, those 2 means, see which one's higher. Or you can just look at the means plot. So I tend to be pretty visual, and you get a means plot out of this. And you can see which group's higher, which group's lower. If it's significant, you know it's a real difference. But, you know, and this, I bring this up because people do this a lot for their dissertation. They like this design. If you get a significant main effect and that independent variable has 3 or more levels, you do need to do multiple comparison tests to figure out, like, okay, which levels differ from which. The one that we learned was called Tukey. So you'd have to click the little box to get Tukey tests to be able to fully interpret the main effect if it's got more than 2 levels. So the interaction effect, there's only one interaction, even though there was 2 main effects. This is how I think of it. So let's see if this works for you. An interaction effect is when the effect of one of the independent variables is different across the levels of the other independent variable. So the effect of being bullied varies depending on whether you're a man or a woman. That's probably what this next thing says. For example, do you think it's possible that being bullied results in higher hostility than not being bullied for just males, but there is no difference or the opposite effects for women who were or were not bullied? So maybe bullying, really makes dudes hostile, but it doesn't really affect women for whatever reason. Maybe there's just different ways they bully too, and they affect you in different ways. Again, Scott's not the psychologist. So what we're essentially saying here is that the effects of being bullied are dependent on sex. This is kind of like the independent samples, a chi-square test of independence, where when you reject the null, you're like, okay, there's some sort of relationship between these variables. So if you get a significant interaction, you're saying, all right, well, it looks like the effect of one of these things differed at the levels of the other, or vice versa. I'm going to have to do some more stuff. So being bullied doesn't affect hostility for females in this example here, but facilitates hostility for males compared to those who are not bullied. So interactions, if you're visual like your professor, they tend to be easier to understand by looking at a picture, and it is sort of just common practice to do a means plot when you do two-way ANOVA, because you get a cool plot out of this. So not only do you get a cool effect of the interaction, both effects at both IVs at one time, plus individual effects, you also get a cool picture. So what's an interaction plot? Well, you've actually been looking at them. So I put some of these earlier in the slideshow. So this is the means plot from her paper. So you got a y-axis here of adult hostility. The blue line or turquoisey line is the females. The orange line is the males. And on the left, that would be kids, people who are not bullied as kids. On the right, you got folks who were bullied as kids. So, it doesn't hurt just to look at these things and see if what you end up interpreting from the actual stats part makes sense, because these are just means, so they should make sense. So it looks like the orange line goes up from left to right, but the blue one either goes down or that's not a significant change. That's what I'm kind of seeing. So left to right, orange goes higher, that's dudes. So it looks like it might be the case that dudes get more hostile when they're bullied as kids. However, for women, that definitely doesn't go up from left to right. So, but it might not be a significant difference. So whenever you're sort of looking at an article or looking at your own stuff, when the lines in your ANOVA plot cross each other, so they actually overlap here, or crisscross, you've probably got an interaction effect among your independent variables. As long as you got enough people in your study, it's statistically significant. Whenever the lines cross, you've got an interaction. So just like with main effects with more than 2 levels of the independent variable, so three or more, you have to do post hoc tests. When you get a significant interaction, you also have to, you know at that point, okay, the effects of one of these variables differed at the levels of the other, or wasn't uniform across the levels of the other. Great. So what was it? Who was more hostile? Well, here you've got to do a series of things. You got to do what's called tests of simple effects for your interaction. So again, if the ANOVA interaction is significant, all you know is that the effect of the IVs was different at the levels of the other IV. You don't know where the differences are. This is an omnibus test, just like all the prior ANOVAs we've done and the chi-squares. So all you know is, okay, something going on here with my variables. So where might those differences be? Well, you got to do these things called simple effects tests, or SPSS does anyway. They are similar to how you have to do multiple comparison tests for one-way ANOVA, 2-piece, that is. So if the interaction is not significant, so you get an ANOVA table out of this, just like you get an ANOVA table for every ANOVA design we've done. If the interaction is not significant, you're done. There's an inadequate evidence suggesting that the effect of one variable differed across the levels of the other. You don't have to do these simple effects tests. But I do want to tell you, on tonight's assignment, I have you go in and blind and just doing them, so you don't have to go back into SPSS twice. So, but normally you would run the ANOVA, see if the interaction is significant, and then request the simple effects test from SPSS. So, yeah, here's something new. So it turns out you don't get them by clicking things in menus in SPSS, but thank God you don't have to do it on your calculator or phone. You get it through something called syntax in SPSS, and this will, a couple of people find this quite interesting. So I'll talk about it when we get there. So researchers, there's more than one simple effects test that SPSS will give you. It's going to give you an effect for each level of one of the independent variables holding the other one constant, and I'll go through and show you an example of that in a sec. But because you have multiple tests on the same dependent variable, that means you've got a lack of independence or a likelihood towards type 1 error inflation. So do you remember Bonferroni corrected alpha levels? You got to do Bonferroni in this. And so if you did, the way to do a Bonferroni corrected alpha level is this formula where it's 0.05, the alpha level you want to keep, divided by the number of simple effects tests you're doing. Sometimes you do 2, sometimes you're doing 3, sometimes you're doing 4. And then whatever that number that comes out on the backside is, that's your new alpha level you use to interpret the significance of your results rather than 0.05. So we actually did do this on repeated measures ANOVA when we did a series of t-tests. We had to adjust the alpha level. So same thing here. So continuing on with simple effects tests of the interaction, it turns out there is more than one set of simple effects tests. So you got to pick them. So there's that same plot from earlier, which is the sex is the lines, and from left to right you're going from bullied to not bullied. Kind of looks like dudes got more hostile, women not so much. So one way to do these simple effects tests is what we call comparing the level of A, first variable, within each level of B. So in this particular analysis, we're saying we are going to keep B, we're going to keep B constant, bullied status, and we're going to compare men and women. So bullied, not bullied males versus not bullied females. That is comparing A here, variable A, which we just designated as whether you are bullied or not, whether you're male or female or not, within those who were not bullied. So that's one test. You do the test, it's going to say, okay, well, it might be the case among not bullied persons, maybe that female means a little bit higher. Maybe women are more hostile if they're not bullied than dudes who are not bullied. I don't know. You never know what you're going to find. It's research. It's exciting, folks. So that's one set of simple effects. The other one that would go between the lines would be on the right. That'd be among bullied people. You've got males and females. So let's see who's more. Is there a difference in hostility among bullied males versus bullied females? So that would be the second simple effects test. So it's called between the lines. I'm hoping that's really obvious, but in case it's not, because what it's doing here is comparing the two means between lines. Yeah. So between lines, you can also request from SPSS the set of simple effects tests that compares along the lines. So what would that be doing? Well, it's going to stay with the blue line or stay with the orange line and compare the two means. So it's going to compare among males, those who are bullied or not, who's more hostile. That's one test. Then among females, comparing those who are bullied or not, who's more hostile. So this would be comparing levels of B within each level of A. So there's one, that would be not versus bullied males. So we're comparing B within level A. And then you've got not bullied versus bullied females. So that'd be along their line. And that would be the second simple effects test. So how do you know which one to pick? Well, when I was in school, they just told us to do them both every time. And, pick the one you like the most, because you don't want to be doing 4 tests. 2 sets of simple effects tests twice is 4 tests. So we would look at which one sort of made it easiest or addressed our hypothesis the most. So which one you pick, it probably depends on what your hypothesis is. And if you get stuck, just send me an email. So let's say you were doing a study where, again, one or more of your independent variables in your between groups ANOVA design had 3 or more levels. Well, in this example, there are only 2 levels in the example. So if a simple effects ANOVA is significant, you know that, well, whatever those 2 levels are, there's only 2 of them, they're different from each other. So go look at the means or look at the plot to see which group was higher or lower as most interesting. Which is what I said there. If you've got 3 or more levels, you have to do multiple comparison tests for your simple effects test. So those simple effects tests are essentially ANOVAs. You have to take it that next level. So simple effects tests for independent variables that involve 3 or more levels, they are omnibus tests, just like one-way ANOVA. You go, okay, there's some sort of difference here among these 3 or more means. What are they? Well, you can use what's called the pairwise comparisons table in the SPSS output, and that will give you like a Tukey-like test. Do remember to use Bonferroni corrected alpha level if you do the pairwise comparisons, because it doesn't actually adjust for automatically like Tukey does, but it is the appropriate test. So just so I can say I told you, if your simple effects test is not significant, whatever means are being compared aren't significantly different. So that's your conclusion. Do not pass go. Do not do your pairwise comparisons tests. So decision rules for determining your statistical significance. For the main effects and interaction, it is one rule. If the ANOVA sig is less than 0.05, reject that null. There is something going on for that effect. That means there is a main effect or there is an interaction, and you know which one it is. If ANOVA sig is greater than 0.05, you retain the null hypothesis. That is, whatever groups are being compared, they don't significantly differ. So for the, by the way, that would be the same for the interaction, same rule. Is it less than 0.05? Cool, I got an interaction. Then you go on to your simple effects test. So the simple effects test for the interaction also have their own rule here. So because those use Bonferroni corrected alpha level, the only thing that's different is you see if the simple effects ANOVA sig is less than alpha Bonferroni. So if so, you reject that null hypothesis and conclude the same thing, groups differ. If the ANOVA sig is greater than your Bonferroni corrected alpha level, those groups don't differ. So again, there's a formula for calculating your alpha, your Bonferroni corrected alpha level. So in the example where you are, say, interested in the effects of variable B within each level of A, well, you're going to be doing two simple effects ANOVAs. So to calculate this, it's 0.05 divided by 2. So it's 0.025. That would be your new alpha level that you would use to interpret your simple effects. So measures of effect size in ANOVA, it is eta squared this time. So eta squared, kind of like with the beach ball earlier, it tells you the proportion of variability in the dV that's accounted for by the independent variables for a particular effect. So you get one of these for each main effect, and you also get one for the interaction. So, and like always, it can range from 0 to 1 or 0 to 100%. Bigger number, that variable is more strongly related to the dependent variable, predicting it. And I learned how to use the fancy formula maker, so now you got a fancy version of this formula, but it just puts in math that the way to calculate it is you divide the sum of squares for the effect you're looking at, you get that from the ANOVA table, divided by the sum of squares total. So I've been putting on these slides, how do you calculate sum of squares total, because it does vary across the ANOVAs. I haven't put it yet because there's going to be good news. So the simple effects eta squared is, it really is the same thing. It's the sum of squares for the simple effect, divide that by the sum of squares total. The sum of squares total for both these comes from your initial ANOVA table. So from your overall ANOVA, sum of squares total is the sum of squares for your first independent variable plus sum of squares for the second independent variable plus the sum of squares for the interaction plus the error. And that gives you the whole beach ball. And so when you divide that, which your independent variable accounts for, by the total, you get the percentage. So do note, you have been duly warned after I say this, don't trust the totals that are on the SPSS output to calculate this. Just add sum of squares IV1 to interaction and error and do it on your own, because it seems sort of random sometimes, but it does frequently, and moving forward, same thing, give you incorrect sum of squares total as a table. Thanks, SPSS. So you got to hand calculate it, but it's not hard. You just add the 1, 2, 3, 4 things in your calculator or phone. So there is APA format, because APA's always got to get their grubby hands in everything we do. And so the APA format is basically what it always is. F, you put the 2 degrees of freedom for the effect and the error. You put the actual F value, round to 2 decimals, then P, less than or greater than, depending on if you rejected the null or not. And then you got to pick 0.05 or Bonferroni corrected alpha level in case you're doing simple effects tests. And then you throw eta squared rounded to 2 decimals at the end. So the good news is everything here except eta squared comes straight from your SPSS output. So good news. All right, so let's do a worked example of this. So let's go ahead and analyze the data from that lady's dissertation. What are the effects of sex and childhood bully victimization on hostility during adulthood? Hypothesis here is sort of two-tailed. Does having been bullied as a child have a different effect on males and females' levels of hostility in adulthood? So not saying dudes are more hostile, not saying that women are more hostile, not saying being bullied makes you more hostile, just saying, hey, I'm going to compare the means. It's a 2x2 design, and see what I get. So again, we went over this. You got sex as your first independent variable, 2 levels, male, female. Then you got bully victimization, 2 levels, bullied, not bullied. Your dependent variables, level of hostility as measured by a questionnaire you had people fill out. It's got some range, but higher scores, they're more hostile as adults. There's the data setup. You've got a column there for each independent variable, and then a final column for the dependent variable. And on the right here, we've got all the means. So there's the descriptors table. This just there is no covariates in this, so you're good with the descriptors table. And this is where you find all the means, which you'll be doing on your homework. Well, there's the tutor way to do it. They're all in that column. So continuing, first stop on the way to hopefully a cool interaction is to do a test of homogeneity of the variance, homogeneity variances assumption. Question here is the homogeneity assumption met? So let's look at the SIG for the Levene's test based on mean row. That's what the name of a row. And there it is. So there's our outputs. The top row there is our based on means row. And we're going to look at that SIG value on the far right, 0.470. Decision rule, if Levene's SIG is greater than 0.05, the homogeneity assumption is met. If Levene's SIG is less than 0.05, homogeneity assumption is violated. What's the effect of that? Decrease in power, type 1 error inflation. ANOVA gives you, depending on how bad it is, can give you garbage results. So what do? Well, you can, again, as we've talked about, use a tighter alpha level. So instead of 0.05, I'm only going to consider things real effects if they're less than 0.01. So getting back to the question at hand here. So is a homogeneity assumption met? It's essentially saying, is SIG for Levene based on mean row greater than 0.05? And indeed, it is. So 0.47 is greater than 0.05. So all the variances are basically the same, or yes, close enough. All right, so let's get to the meat of this sucker. Is there a main effect of sex on hostility? So hostility here is the dependent variable, as you shall recall, and sex is the independent variable. So is there an effect of sex just on hostility overall, regardless of any other variables in the whole world or universe? That's the one that this hypothesis is testing. So where is this sucker? Well, it all kind of comes from the same monster size ANOVA table where they just putting more crap in these things. So I have started, intentionally giving you permission to cross stuff out. So just cross it out. That's what the point of me doing on the slide is, because it's just visually too much. So can we reject the null that males and females are equally hostile? So that's the null tested by the main effect of sex. There is our row in here that's named after the independent variable. So that is our row for the main effect of sex. And it's the usual thing here. We'll go over and look at SIG. There's our decision rule. If SIG, the SIG for sex or sex SIG is less than 0.05, you're going to reject the null. If it's greater than 0.05, you're going to retain the null. Our decision here, 0.5 is basically a coin flip. That's definitely not less than 0.05. So 50% is not less than 5%. So what do we conclude? There's no sort of overall difference in hostilities between men and women. So that's another way of saying there is no main effect of sex. Another way of saying it is in the yellow box here. The evidence suggests that male and female adults are similarly hostile, or equally hostile, you could say, ignoring whether or not they were bullied. That's not even taken into account in these. All right, let's keep going. So no main effect of sex. Well, there's another main effect, right? Is there a main effect of bullying? I mean, here's a significant one. Let's find out. Same table with a bunch of stuff in it. See a row in there called bullied status. That is the row we're going to look at. Can we reject the null? That adults who were bullied and not bullied as kids are equally hostile as adults. There's our row. 0.042 is our SIG. So is 0.042 less than 0.05? Let's see what our rule is. So our rule is if bullied SIG, in this case, because bullied is the name of the row, is less than 0.05, yeah, we're going to be rejecting that null hypothesis and say, yeah, one of these two groups is more hostile than the other. If it's sig's greater than 0.05, just retain the null. That is no difference. So in this case, 0.042 is less than 0.05. So there's definitely a overall difference in hostility between people who are bullied or not. So because there's just two levels, we don't have to do Tukey or anything funky. We just look at the two means and see which one's higher, which one's lower. So again, another way of putting this is the evidence is too overwhelming that adults who were and those who were not bullied as children differ in mean hostility, and that is one heck of a sentence. So specifically, the adults who were bullied as children, their mean was 9.45. If you go up to the means table, they're more hostile than those, meaning adults who were not bullied, at 8.27. All right, so finally the super fun one, you guys. Is there an interaction of sex and bullying on hostility? So there was no main effect of one of them. There was a main effect of the other. This says, but if you put them together, you get something more than just the sum of their parts. That's what an interaction is. So same table. Yeah, there we go. But you look at the row that's got both variables named with a star. Star means by or X. So it's kind of like a sex by bullied status. So you'll never guess what we do. Well, let me get the rule up. If sig over there on the far right is less than 0.05, we reject the null. There's simple effects test to do. There's the effect of one independent variable differs at the levels of the other. In this case, yes, it's definitely significant. So the evidence is too overwhelming that bullying differently affects men and women's hostility. Note in that sentence, it's got bullying. It's also got sex involved. So it involves both independent variables. Any true hypothesis would have them in this case. So because the interaction of the ANOVA is an omnibus test, we got to do some more stuff. We got to get the simple effects test to determine, which exact groups mean from each other. Do they all differ? Is just two of them? Like, what's going on? So keep going. I just wanted to tell you that when you see this on your output, we actually use this for ANOVA, but for this one, just ignore it. You do have to pick options on the assignment that end up with SPSS spitting this out, but just know you can cross it out for this assignment. So let's talk about simple effects tests. We're getting there. So interaction simple effects tests, you get them through something called syntax. So you get to syntax by going into SPSS, picking your menu items, and instead of clicking OK, you hit paste. And if you hit paste, it's been secretly writing code behind your back the whole time that you've been using SPSS. And so it actually will just export your code. So it is explained on your output. You have to add a little tiny thing. You got to actually type a couple words here, compare and bullied status. And on the row that is got the interaction effect on it. So you got compare. Name of the independent variable you want to compare across the levels being held constant of the other one. So that will get you the along the lines set of simple effects tests. So this is what it looks like when you click paste. It sort of spits out this like sort of colorful code. See that line in there that says E means equals tables, sex by bullied status, or sex times bullied status, compared bullied status. That's the row you got to do something with. So it normally doesn't have the compare bullied status. That's something you actually got to type. So not too bad, honestly. So you hit a different button and type two words. So let's keep with our theme of simple effects test for the interaction. So here we are comparing those who are bullied versus those who are not bullied. And we do that separately for males and females. So it's bullied males versus not bullied males, bullied females versus not bullied females. There's our plot. We've seen multiple times. along the lines here would be, all right, so we're going to compare not bullied and bullied among males. I think I actually told them to go with this because of the code we were using. But anyway, so that is the along lines one simple effects test. There's also another one. So it's going to compare not bullied and bullied among females. So along the lines, and again, how do you know which one's right? Well, our teacher just had us do them both. Um, it's like, seems like it's kind of strategy you get scolded for in your dissertation defense. So I don't recommend that. Try them, find which one gives the result that's most goes along with your expectation, your hypothesis, or is easiest to actually explain to people on your committee, etc. So just a reminder, y'all, because we're doing two simple effects tests, we do have to adjust our alpha level using Bonferroni alpha correction. So in this case, 0.05 divided by 2 would be 0.025. So let's interpret our simple effects tests. They're in this table that's just, I mean, I know what it means, but you guys probably are going to think it's awful in its naming. It's called the univariate test table. It's been on the output this whole time. So this is what it looks like, which is also not super desirable. It's just a skinny little table that's pretty darn close to your references or whatever your final section is. And you get a row for male, a row for gender, and inside there's actually multiple rows. So I'm going to cut to the chase on this. We're going to look at sig. So we're going to look at the significance value for male and determine if, again, what's that test actually comparing? Well, everyone's a dude. That's actually a constant. It's comparing those who are bullied or not. How would you know that? Try reading this awful note below the table. This is like my favorite bad footnote to ever exist. Each F tests the simple effects of have you ever been bullied at school? Okay. Within each level combination of the other effects shown. Wow. So, good luck with that. So, that is a table note you'll notice in the APA example write-up you don't have to include. So, keep going. So, for each of these, make sure you use Bonferroni corrected alpha level. In this case, the sig over there on the right is going to be less than 0.025. Again, these tests are only going to pop out if you hit syntax and add some code. So just to show you the means, because we're about to interpret some stuff here. So looking down the SIGs, you can see that the SIG for male is 0.006, and these guys started putting the leading zero on. It's already a long enough lecture. I won't rant. So anyway, 0.006 is less than 0.05, so this guy might, or we would conclude that there's a significant difference between males who are bullied and not bullied, based on our Bonferroni corrected alpha level 0.025. So, all right, like who's more hostile? You just look at your means there. So you got to find the overall mean for people who were bullied and the overall mean for people who were not bullied. And let's do it. So bullied versus not bullied males. Remember to use alpha 0.025. There's our sig, it's less than 0.05. Let's find our means. So we got males. What are those two rows there? No and yes. Well, the question was, have you ever been bullied? If you look at the top of the table. So no is non-bullied people. Bottom one is bullied people. Those two means, SPSS tells us, are significantly different. Something like 3 points different if you look at them, 3.5. So, which group was more hostile? Well, the yes is, which is those who were bullied. That's the first effect from our interaction we interpret. So, any of the other differences significant? It's a good question. Let's find out. So, males who were bullied were more hostile than males who were not bullied. We said that. What about those who were bullied versus not bullied among females? So the same two independent variable groups, but we're comparing, they're different people in the groups. So anyway, there is our SIG. SIG is 0.99. It's pretty hard to get closer to 1.0. Anything, question is that less than 0.05? No. 0.99 is definitely not less than 0.05. So there is no simple effects test that's significant for females comparing those who were bullied and not. So females, one way of shorthanding this is the hostility of females was equal to, among those who were bullied was equal to those who were not bullied. So here's sort of my overall take home from this. Overall, men who were bullied as children, they had a mean of 10.40. It's still shown in the table. They were more hostile as adults, or they are more hostile as adults than people who were not bullied as a kid, among males. Now, among women, women were equally hostile. So remember, it wasn't significant. So that tells you whatever we're measuring here, it's not significantly different. He's like doing some special tests this weekend, so he didn't go anywhere with the boss. So what do we got? Well, we know there is no significant difference among women who are bullied or not. Bullying doesn't have the same effect among women as men. That's like your big take home. So you do get a cool picture, as I said. So get to bust one of these out, fill up your dissertation, hit that length margin, or that sort of, they won't tell you what the length is, but there's obviously a length thing. So you just click plots to get this, put stuff on the right row. So bullied men were more hostile than those who were not bullied. It's kind of, if you watch this, it's cycling through several graphs. It's actually a little hard to figure it out, but he threw these sticks down. It's kind of a long story. Some other time. So we got people who are bullied. Bullied men who were more hostile than those who were not bullied. That would be the main effect if you look at the mean. So remember, they're 10 point versus something that was 2 points lower. So, however, we also did a second simple effects test. And that is, there was apparently women in the trunk, or a woman, and they actually did a special medal in her honor this weekend, or this month, sorry. Anyway, scooting on. We got to get those measures of effect size. Good news is it's basically the same formula. So you got to get sum of squares total by adding all this stuff together. Once you get it, you can use it for most things. There is our summary table from a couple seconds ago. I'm just showing you where the means come from for for calculating the sum of squares. Like where do they come from? This shows you where I got them in the table. There you go. If you add all those up, apparently it's 3,248.087. So that's the number you get. So just this is not the same eta squared. So in between when these slides were originally created, there were some people I'd let use them. They took over when I went to grad school, but something's funky with a couple of the values in here still, unfortunately. Yay. Scooting on. So sex alone, remember it wasn't significant, accounted for 0.3% of variability. Bullying alone, this is the main effect of bullying, accounted for, if you scooch the decimal over twice to the right, 2.3% of the variability. And there's our interaction, also significant. So our interaction is 0.023. Like if they use precautions at the school, then hopefully they don't shave your head and you were just teasing me. So, all right, so it wouldn't be a Scott later in the class assignment if we didn't have barfing Nessie, right? So you got to copy the stuff from this table that we keep seeing, that stuff specifically, into an APA format table. There's our good friend barfing Nessie, barfing Skittles for no reason. And again, everything except eta squared comes straight from the output, but the stuff for that comes straight from the output. You do have to hand calculate the total and the degrees of freedom. Don't use one of the ones laying on the ground if they're sitting around there. Like, should be picking up that stuff anyway. But you just got to add a couple numbers together. You will always be right. All right, final slide for this week. So the APA format for simple effects tests. So there's that univariate table again. We use the usual F, degrees of freedom equals the number P less than or greater than eta squared. So this example for bullying within males, that first simple effects test up there, I filled in 1 and 174. The F value is 7.76 rounded, sig is less than 0.05, and calculated eta squared. For females, you can see it's basically, there's a F is 0. So that was one that was like super not significant. Where's that stuff come from? Well, here's some doohickeys that kind of show you where it comes from. And as promised, it's all from the table except eta squared. So eta squared, you've already calculated it. No, you actually haven't, right? So you got to get your sum squared totaled. It is the sum squared total that you've already used, so you don't have to recalculate. It's the same one you used to calculate the eta squareds for the main effects in the interaction. So here we go. You take that 137 from the table on this page, divide it by that same number that's back on the slide. You get 0.042 or 0.04. And it's just straight up 0 for females. So that is your introduction to two-way between subjects ANOVA, and you get some fun doing one of these. So.